I don't know if you know this, but when the R2000 program, which was called the SEED program in those days, started, they brought in folks to do training, and Oliver came in along with Harold.
Oliver
Durer. And many of you would know who Oliver is, and those of you who don't know him, he's worked with home builders and CMHC's worked as a builder. Harold invited Oliver to join him at his investiture. Which was a thrill for Oliver. And I couldn't make it, and I said to him, would you like to write a note? And so this is Oliver's note to all of us and to Harold. Dear Tex, many thanks for the opportunity to contribute my best wishes to all the good folks at Spring Training Camp, and particularly to Harold Orr, member of the Order of Canada. The Order of Canada is a singular honor granted to an individual who personifies the motto, they desire a better country. Someone who has made Canada a better place to live as chosen by her citizens, and as such represents the people's nobility. Harold epitomizes those virtues. He has affected the way people build houses across the country and worldwide. The Order of Canada also reflects represents a glory reflected, the order being granted to an engineer, a building scientist, one of our own, who has pioneered the technology on which we have all labored, some of us for decades, is something reflects on all our industry and to each of us individually. When we started this adventure, there was perhaps a couple of hundred people in Canada who could construct an R2000 home. Today, there isn't any builder that can't. And most importantly, everybody in North America and increasingly worldwide can find easy reference material and training courses to supplement that lack of information regarding insulation, airtightness, combustion air, and ventilation. That is predominantly down to the people gathered in this room at Spring Training, among others. Greetings to you all, and please permit me to join with you in congratulating Harold Orr.
So Oliver got to attend, and now you guys get to attend. Andy, just play from the public record if you wouldn't mind. That sound?
This is your investiture.
Harold Walter Orr. Harold?
I want to savor the moment.
Oh, for heaven's sake. It worked fine.
All right, who's having the bandwidth?
Oh. Well, it was a good idea.
Have been integral to improving energy efficiency and conservation in Canadian homes. As a housing engineer with the National Research Council, he was a key driver of the Saskatchewan Conservation House Project, which led to the establishment of new national energy conservation protocols for Canadian buildings. His innovations, which include new insulation techniques and materials, air sealing and efficient ventilation, blower door testing, and heat recycling, serve as a worldwide models for energy efficient housing. Mr. Orr.
And that's Julie Payette.
And what I'm saying there is from one scientist to another, thank you.
From one scientist to another, thank you. Bravo.
So when Harold was invested, it was quite an adventure because the planes were all socked in because of a snowstorm. And in fact, Harold, with his party of, there were 4 of you all together, they said they could get him out the next afternoon. It was a Friday afternoon, but the investiture was in the morning. So off to the car rental, and in the snowstorm, the 4 of them headed up to Ottawa. And he missed the party that was planned at CHBA. And CHBA, let me bring Sonia up. And Sonia, on behalf of CHBA, has something for Harold.
So yes, we wanted to take the opportunity. We wanted to take the opportunity while Harold was in Ottawa to congratulate him ourselves. And CHBA has wanted to recognize you with a Lifetime Achievement Award. And that was why I was trying to get you to come to our conference, because I wanted you to come get this again, because we missed it because of the snowstorm. So we wanted to say thank you so much for all of your work. We really appreciate it.
Well, thank you.
Sorry. Thank you. Thank you.
Oh, dear. How do I follow that? Let me tell you, really, I started out as a lowly carpenter.
As a carpenter. Sorry. I just gotta get this closer.
I started doing carpenter work when I was about 12 years old. You know, working with my father, who was a carpenter, and I was go and get this, and go and get that, and go and get something else. I go for it, you know. And my father was a carpenter. My grandfather was a carpenter. My great-grandfather was a carpenter. And my great-great-grandfather was a jointer. Did finishing work. So I come from a long line of carpenters, and I grew up doing carpenter work, like I said, from the time I was 12 years old. When I started university, I'd been doing carpenter work, and I had put enough money in the bank to earn my tuition for the first year. And I was doing carpenter work, did carpenter work in the summertime to put myself through university. It's a long story. Things, we have the Saskatchewan Conservation House. And I'm sort of noted for that because I was asked to sit on a committee to design a solar house appropriate for Saskatchewan. This was back in 1977. And we did some preliminary calculations on the back of an envelope. And we were astonished because in Regina, where we were going to build this house at 50.5 degrees north latitude, there's not a lot of heat from the sun. So how are we going to heat this house? And so we did some calculations, and you know what? We got an Olympic-sized swimming pool of water to store the heat from the summer to keep the house for the winter. And in fact, in Toronto, they were trying to do some of the same thing. And so north of Toronto, and I don't know how many of you have heard of the Provident House?
Provident House?
Provident.
Provident. Is that familiar?
No, when I saw
You won't
Richard
even-
nodded his head.
You won't even find it on Google anymore. But north of Toronto, they decided to build what they call Provident House. And it's an A-frame house with the south facing, the wall facing south. And it had a total roof system of solar collectors, and these water-cooled solar collectors. and they had the whole basement as a water storage tank. And I went into the house, I went up and had a look at it, and the humidity is about 100%. Ooh. And I think they misnamed the thing. They should have called it the Prove It Don't Work House. Well, we were asked at the same time to design this house for Saskatchewan. And we came to basically the same conclusion, that it wasn't possible to do this. And so we said, well, look, what can we do? We can reduce the heat loss from the house very significantly. Let's try and do that. And my specialty was in terms of air tightness of the structure. So I knew how to build houses tight. And so I said, I will put the vapor barrier, which we were using to make the house tight, I will personally put the vapor barrier in and make the house tight. And we did. This house, when we built it, was likely at that time the tightest house in the world. It had a air change rate of half an air change per hour at 50 pascals. Now, how many of you have built houses that are tighter than that?
Tighter than 0.5.
Tighter than 0.5. 1, 2, 3, 4.
7 or 8, yep.
Yep, 7. Very good.
That's pretty good of you guys. Harold just applauded your work. Write that down.
Anyway, somebody brought up on the committee, they said, how much insulation should we be putting in the house? Because remember at that time, R7 was the standard insulation. You put R7 flat in the walls and maybe R10 in the ceiling, and that was it. And somebody suggested, well, why don't we use 2x6 studs and put R20 in the walls? And I said, well, I know of several people who have done this, and they are not getting the bang for the buck that they had hoped to achieve. And I said, I think what we need to do is have at least R40 in the walls and R60 in the ceiling. So we went ahead and designed the house, and we got it all designed and sent the information back to the government who had asked us to do this. And we told them, here is our prescription for your solar house that is appropriate for Saskatchewan. But it's a conserving house. And they came back to us and they said, that's fine, make it conserving, but put solar energy on it. So the house cost, this is 1977, the construction cost of the house was $60,000. The solar system, which you can see up at the top there, is hot evacuated tubes, thermal solar collectors, and it has a 2,000-gallon tank in the back to store the hot water from this. The system costs $65,000. Something's wrong here. Anyway, it gets worse because the maintenance cost on the solar system the first year was $10,000. And the maintenance on it the second year was $5,000. And the third year, the house was sold and the new owner took the solar system off. Anyway, so been a long road. Anyway, what we did for the house, we built a double wall.
Go with the double wall.
We built a double wall house. The inside structure was a 2x4 wall. This shows a 2x4 wall as the outer wall, which we did. But the outer wall is the structure on this house, and the inner wall was a partition that was put into place after the outer wall was made. And then we put in the 3 layers of insulation. Actually, we used an R12 on the outer wall, an R20 between the 2 walls, and an R12 on the inner wall. And then I had the problem of going in and putting in the vapor barrier and sealing it around all the electrical things and whatever. Oh, nasty. But we got it done, and after we had done this, we wanted to see how could we do this better. Well, what I've done better is what we call now the Prairie double wall, and I would recommend it to you. The Prairie double wall, instead of having the outside wall as the structure, has the inside wall as the structure. This means that the floor joists don't have to span so far, the roof trusses don't have to span so far, so you can have a bigger house for your buck. No extra cost for that. And the outer wall now can be a light frame. It doesn't have to have any of the structural components around windows, doors, headers, cripples, and all this sort of thing. It can be a light frame to make space for the insulation and hold the siding on. Now, the only thing different what we do here than what there is that when we make the outside wall, which is framed on the floor, we square it and get it in position, and then while it's in ready position, ready to put sheathing on it, as we normally put on the outside wall of a house. This is the inside structural wall now. We put the vapor barrier on the top, and then we put sheathing on it. And I hate paying $13 for a sheet of OSB, but that's the way the market is right now. I'd prefer to pay $5 or $4.50 for a sheet of something that I could put on to hold the vapor barrier. We put that on, and then we use that as a jig to build the outside wall on top of it, so that the windows match the same spot and the doors match the same spot. And then we lift it up to make the space between the walls, put it on temporary blocks, and put a strip of plywood or OSB at the top and a strip of plywood at the bottom of the wall to hold it in its final position. And we also line all the windows and door openings with this to hold the walls in the proper position. And then we can now insulate between the 2 walls and insulate the outer wall. And then we put sheathing on the outer wall and stand it up in position. Now the vapor barrier then comes to the inside of the wall, and we can join it with the vapor barrier from the floor below, the vapor barrier from ceiling. And it has another major advantage, and that is that this wall is now 3/4 of an inch taller than the standard outside wall. What's that advantage? Well, it means that we can put the roof trusses on, and then we can go in and put vapor barrier and drywall and ceiling as large pieces instead of the little scrap here, little scrap there, little scrap there, and all the cracks and joints and all the rest of it. And I watched 2 men putting a drywall on a 1,400 square foot house bungalow in 2 hours. And when they got finished, they picked up all the scrap in one hand, walked out and dumped it in the garbage. And when you do this on a normal house, you have enough scrap that you can fill a half-ton truck. That's money in the bank. The other thing is, with the vapor barrier on the outside of the inside wall, the vapor barrier is now 3.5 inches away from the idiots with the drywall saws and the knives. And that makes a major difference because, and it's away from the electricians as well. And so the electricians can save bundles of money doing it this way, whereas if you have the vapor barrier right on the inside, you have to poly pans, and you've got caulking compound, and you've got oh my goodness, and all the time and bother involved in putting all this together properly. And then you also have all the leaks. As a result of this, we had a builder in Winnipeg that was building houses with the Prairie double wall. And they had a trick in doing this. What they would do is when they got to the stage where they could do a blower door test, they would invite the other crew that was doing the same type of house to the house to witness the test and tell, how did it go? Well, the result was that these two crews would work against each other, and they were routinely making houses at 0.1 air changes per hour. Has anyone built a house with a 0.1?
Error barrier.
I think it's an opportunity. Now, how about costs? Well, I have a spreadsheet there in my possession showing the double wall, and the current construction which we're using is 2x6 with 1.5 inches or 2 inches of styrofoam on the outside. You know what? The double wall gives you at least twice as much insulation, and it's cheaper.
Of interest, Gene Myers, who you met earlier, Gene does a double wall still in Denver. That's the way he builds his wall. For a slightly different reason. Is Gene in the room? Where's Gene? I'll tell the story for him. He would say he does a double 2x4 wall because it's tough to get framers. And he said the framers, if you make them do insulated sheathing, they don't want to be on the job site. So, right. And he calls it a dumb tax, and they charge him more. So he said, I just tell them to build one 2x4 wall. When they're done that one, I just tell them to do another one. And he said that's easier than trying to get them to change what they're doing. So he's still to this day doing double wall.
Yeah. So anyway, it really bothers me. I see this all the time. I drive down the street and I see somebody there tearing the old siding off their house, and I know what's happening. They're trying to upgrade their house, and so they take the siding off, and what do they do? Well, I've seen them put anywhere from 3/4 of an inch to 2 inches of styrofoam on the outside, and then they put tieback on it and so on. This bothers me a great deal because the tightness of the wall has to be inside, needs to be inside. The vapor barrier needs to be inside of this. And 2 inches of styrofoam isn't enough insulation to keep, if you put the vapor barrier on the outside of the structure, isn't enough insulation to keep that vapor barrier warm enough so it won't cause condensation on it. So what they do is they put styrofoam on, and then they put tieback and new sheathing on. By the way, tieback, if you make a box of tieback the size of your house and do a blower door test on it, it won't pass your current standards. Tieback is not an air barrier. Air goes through it quite freely. Put that in your pipe and smoke.
Holy mackerel, was that a lawsuit?
Anyway, no, I think tieback has its place. It makes an excellent wind barrier to prevent wind from blowing into the outside cavity of the wall and around the house and so on. But it's not a vapor barrier, and it's not an air barrier. If you do the test on it, it will not pass housing standards as an air barrier. Now, so what I'd like to see is, and what I've done numerous times is, I take the siding off the house, I wrap the house with poly, and I seal the poly to the foundation, and I go up to the top and I seal it as carefully as I can to the top plate all the way around the house. And then I take 2x4s, and if it's the rafter is sticking out there, or the rafter sticks out, I nail the 2x4 to the side of the rafter and hang it down to make me some space. This wall is now supported by the rafters. It doesn't need to be supported by the bottom. I can hold it out with a piece of plywood at the bottom and a bottom plate, but it's supported from the top. Now this, how much space did I want to put? You can put a 3.5 inches, or 5.5 inches. You can do 7 inches. You can do 8.5. How much did you want to put in there? And now you can fill this outer space where the 2x4 is with insulation. And do you know what? This is cheaper than putting 2 inches of styrofoam on the outside. And it's got the advantage of being much tighter, potentially much tighter, and secondly, it's got way more insulating value. And we got much more bang for your buck. Okay? But it really bothers me when I see them putting this 1.5 or 2 inches of styrofoam on the outside. What happened to the tower building in Prairie? You heard about the story about the tower, and they had a fire on it? And the fire went up the outside. Why? Because they had put 2 inches or 3 inches of styrofoam on the outside and a light cladding on the outside. It caught fire and went up through 9 stories of the building and burned down.
So that's the story of Double Wall. That's pretty interesting. I'd like to hear the story, if you're okay, on blower door testing, how you got to. I was going to click a little bit here. I wanted to see high levels of insulation and then very well sealed roofs and walls, 0.8 at 50. Tell us a little bit about how you arrived at
One more. And a couple more.
Couple more, sorry.
Next slide is where you're headed.
Okay, Gordon, more air, better airtight.
Better airtight. I think we're still okay.
Well, when I was taking my engineering degree, and we were doing calculations on heat loss in buildings, and we would take the area of the walls and its R value, and we could calculate the heat that would go through the walls. And we do the same with the ceiling. We calculate the area of the ceiling and its R value and the temperature difference across it, and calculate the heat loss to the ceiling. We could do this for the basement. But when it came to air leakage, we wet our finger and say which one. We grab a number out of the air and quickly write it down before we lost it. Literally, that's what we did. We just took a wild guess at what the air leakage was going to be. We had no idea. ASHRAE had some standards for how to do this, and they suggested you get a feeler gauge and you go to the windows and you feel and measure the cracks around all the windows and around the doors. And then they had a sort of a formula to what's the wind effect on the building and what the wind pressure is going to do. And this is a window opening, and you're going to calculate now how fast the air is going. When you did this, it was a very onerous problem. And the result was, when we got finished, we knew from experience that the heat loss due to air leakage was much greater than that. That wasn't nearly enough. So as I wrote my thesis, and got my bachelor's degree, it was suggested to me that I should go on for a master's degree. And the professor I was working with, Dr. Green, suggested, why don't you design an instrument to measure how fast the air is changing in a house, in a building. And so I undertook to this. I did a lot of research on this. And we decided to use a tracer gas, and the one we selected was helium. And what we would do is I built an instrument to measure how much helium was in the air. And the first year it didn't work, so I didn't get my degree. And because how do you write a thesis that says we did this but it don't work? So I went at it the second year and I made some major modifications to it, and we did get it to work. And I wrote the thesis, and when I got my degree, I was doing the work at the National Research Laboratories of the National Research Council because the university didn't have the equipment I needed. And the National Research Council did have the equipment, so I was doing my work over there. And so when I got my degree, Gus Handigard, who was the head of at that time, hired me to work at the National Research Council, and what did I do? Make this equipment better. So, okay, I went on and I spent close to 7 years on this instrument to measure infiltration in buildings. One of the first things we did was, the problem was with the helium. When we put 100 cubic feet of helium in the house, the concentration was high. And as it went down, when it was high, it went, some of this went into cupboards and closets and extra rooms and basements and so on. And as it got down, it would come out of the woodwork. And so what are we measuring? We're measuring the level of helium. Goes like this, you know. But what has that got to do with the ventilation in a house? Because we don't know how much is being stored, and we don't know how much is coming out of the woodwork and all the rest of it. So we got to change the way that this work is working. So one of the things we did was to change the tracer gas from helium to sulfur hexafluoride. Now, I don't know if any of you know what sulfur hexafluoride is. But it's a tasteless, odorless, colorless gas. It's easily liquefied. And we could do the same test that we were using 100 cubic feet of helium with 1 teaspoonful with 5 cubic centimeters of sulfur hexafluoride. And since we're using such a small amount, we could change the process so that we were using a constant level of tracer gas in this place. And since we knew what the concentration was and how much we put in, we could now calculate the ventilation rate of the building. And we were using a gas chromatography instrument, which we took one of the first computers available to do physical work that you could program to do physical work. And we programmed it to, first of all, take a sample of the gas, put it through the gas chromatograph, read the peaks as they came out, separate the one for the sulfur hexafluoride, calculate what it should be, and then inject enough to bring it up to the proper level, and then it would repeat and do this again. And this equipment, we got it into a 19-inch rack. It was about 5 feet high and 24 inches the other way. It'd take 2 men to take this out of the back of the vehicle and put it down in the basement and hook it up. Took a half a day to get it hooked up and get everything working. And we'd run this for a week. And when the week was finished, then we had to go back and take it all out and get it. And one afternoon we were thinking about this and said, there's got to be a better way. And we were familiar with what was happening in Ottawa. Our people, George Chimera was working in Ottawa on finding out where in the world are the holes in a house. And what he was doing was he was taking sheets of poly and covering the windows and then measuring had a fan system which you would pressurize the house and measure the flow through this. And he'd cover the windows, and then he'd cover the roof, and then he'd cover the walls, and try and find out where the holes were. And what he was doing, he had put a piece of plywood in the basement window, and it had a 12-inch diameter duct that went 20 feet out in the backyard. And then he had a fan out there which he would control the speed, control the amount of airflow through the house. And to measure the airflow in the duct, he had a hole in the side of the duct and put a pitot tube in there, and he would divide the duct up into 10 equal spaces and measure the centroid at each of these spaces. And then he'd average these up, and this gives him the airflow at that position. And then he'd change the speed of the fan or something, the airflow, and do it again. And after he'd done this 10 times, he'd then plot this out, and this gives him the size of the hole in the house. And I said, there's got to be a better way. Agricultural engineering in Saskatoon was doing tests at the same time on gasoline engines, and they wanted to know how much air was going in the carburetor. And they had a very simple system. They had used a smooth edge orifice, and they had pressure caps around the throat of the orifice. And there's a simple calculation that you take the pressure there and you calculate, and it tells you how fast the air is going through. Very simple. Take one reading. It's done. So, we had a catalog from Princess Auto in Winnipeg, and they were selling surplus war material. This is back in 1980. They're still selling surplus war material. And they had a 9-inch vane axial fan. It's 9 inches in diameter and 9 inches long. It was operated on 28 volts DC. It ran at 10,000 RPMs. It's a real screamer. And we bought this, I don't know, it's about $45 or something like this. We got a piece of plywood, we cut it to the size of the door. We cut a hole in the center, mounted the fan in the center of the door, and I made a power supply so we could vary the voltage on this DC motor, so it's very easy to get a variable speed on it. And we put a manometer on to measure made a 5-inch throat for this. And here's our blower door. I wrote a report on it. I have a copy of it there. And if you'd like to see it, I wrote a report on this. I published it, and people somebody from Minneapolis saw this. They came up to Saskatoon, saw our door and so on, went back to Minneapolis and started manufacturing Minneapolis blower doors. Well, we made the door a little more complicated. We cut the door into 3 equal pieces and put piano hinges on. This means we can fold it up and stick it in the back of the car. And we actually put a 4-inch piece on the side so that we could fold it back and get a 32-inch door, or open it up to a 36-inch door. And I flew over the country with this thing. I took it up to the Yukon, and we went out to visit a house. We put it on top of the roof rack, tied it down. We drove out.
But it was only $45 worth of injury. We should, we're close to time, and it wouldn't be wonderful if we had more time. The good news is we do. Harold, you'll be around this evening. Anybody ever used one of those big wooden blower doors? I did. The very first day I did blower door testing, I did 3 houses with it, and then realized there's got to be a better way. Apparently not. So we're still doing that. I had the pleasure of introducing Harold down at EBA, Energy Environmental Building Alliance in San Diego, The award was a legacy award. It was supposed to be delivered by the Passive House folks. She, unfortunately, Katrina couldn't make it, and I was asked to step in. So simultaneously, Harold, in the last 6 months, has been honored, Order of Canada, has been honored by the U.S. groups that do energy efficiency and the Passive House groups who consider him father, frankly, of the Passive House program. So quite the legacy. We probably have time, perhaps, for one or two questions. Anybody have a burning question?
Just a quick one. This was the birth of HRVs in this house, Saskatchewan Conservation House. Last night at dinner, Harold was telling us how Rob Dumont did some calculations and he worked on them, and it worked into Hot Cam, and that became Hot 2000. So everything that we're doing now has much of its roots in the house that Harold and his team worked on, which is pretty bloody amazing.
How many of you?
You were going to ask her how many?
How many of you use Hot 2000? Oh, my.
Matt, put up your hand. You're not just maybe half a hand up. Matt. You're not that good at it. So I have to dig back.
I think we'll throw some tomatoes, but he had a lot to do with acoustical sealant too.
Anyway, how many of you know of a computer program that's over 40 years old that's still in use?
That's amazing in itself. Absolutely. Yes. Well, again, Harold, so much. Thank you very much for being here and sharing some stories. And Harold will be around this evening if you'd like to hear more. And Andy, perhaps you'd like to come up and we'll just kind of finish up the day. Thank you very much.